Secondary research, meta-analysis. A meta-analysis combines the studies using a quantitative index to develop a single overall estimate of the intervention effect. The terms systematic review and meta-analysis are often used interchangeably, but they do have different objectives. While both present a critical appraisal of the studies, only the meta-analysis includes a statistical synthesis of data. The major advantages of meta-analysis are 1. To increase power by increasing sample size. 2. Improve estimates of effect size. 3. Resolve uncertainty when conflicting results occur. And 4. Improve the generalizability of findings. Individual studies may have non-significant findings because of small sample size. Therefore, combining samples from several studies has the potential effect of increasing the ability to detect important differences. The degree to which studies in a systematic review are similar is based on the heterogeneity of the treatment effect across the studies. This heterogeneity can be due to two main reasons. Either it is a random effect due to chance differences between studies, or study samples may be drawn from truly different populations. The statistic used most often to test for heterogeneity is chi-square. A non-significant test indicates that there is a common treatment effect across studies, and therefore the observed differences are what would be expected by chance. A large chi-square value indicates that a common treatment effect is unlikely. You are expected to understand the concept of this test, not the test itself. The concept of effect size is central to meta-analysis. Effect size is an estimate of the magnitude of difference between groups of the effect of the intervention. Effect sizes can be obtained for continuous data, such as means or correlations, or binary data, such as relative risk and odds ratios. Estimates from individual studies are combined to reflect the overall size of the effect of the independent variable. The larger the difference, the greater the effect of the intervention. Meta-analysis does not pool subjects into a single sample. Rather, each study adds to the estimate of the population parameter by contributing its sample effect size index. The result is usually a more precise overall estimate. On this slide, we are referring to continuous data. Typically, means and standard deviations are calculated with this type of data. There are several versions of mathematical equations used to calculate effect size. One of the most common is Cohen's d, which is written on this slide. Also presented on the slide is a general consensus of an accepted classification of effect size values and their interpretation. Now consider ordinal data. The most common measure of relative effect is relative risk, which indicates the likelihood that someone who has been exposed to a risk factor will develop the disease, as compared with one who has not been exposed. Relative risk is defined as the ratio of incidence of disease among the exposed subjects to the incidence of disease among the unexposed. Measures of relative risk are appropriate for use with cohort studies. This is how meta-analysis typically reports their statistical data. This is called a forest plot. The outcome of each study is shown by a small square icon, which represents the relevant outcome for the study. Each horizontal line represents the confidence interval around that estimate. The size of the square corresponds with the 8 of the study, which is related to the sample size. The larger the sample, the larger the square. The confidence interval for the total combined value is indicated by a diamond shape at the bottom of the plot. The center of the plot indicates no difference between groups. To illustrate this process, we will consider a meta-analysis by Panpanich and others to study the effect of antibiotic azithromycin compared to other antibiotic agents for the treatment of acute lower respiratory tract infections. They found 14 trials that met their inclusion criteria. Through pooled analysis, they show a relative risk of 0.96 for clinical failure associated with azithromycin. A relative risk of 1.0 indicates no excess risk associated with the treatment. In this example, a relative risk of 0.96 is close to 1.0, and indicates no substantial difference in clinical failure with either treatment. A relative risk of less than 1.0 indicates a reduction in risk associated with the intervention. The first column lists the studies by first author. Columns 2 and 3 indicate the number of subjects in experimental and control groups. Lowercase n equals the number of adverse events. Capital N equals the number of subjects in the group. For example, for the study by Balmes, 1991, the total sample was 104 subjects. 11 subjects had adverse outcomes. The graph illustrates the relative risk of clinical failure associated with use of azithromycin. The outcome of each study, in this case, relative risk, is shown by a small square icon. Large squares represent larger sample sizes. The size of the square corresponds to the 8 of the study, which is related to sample size. Confidence intervals are shown by the horizontal line and in parentheses in the last column. An arrow at the end of the horizontal line indicates a value that goes beyond the scale on the plot. The next column shows the weight of the relative risk based on sample size. The diamond on the plot indicates the overall relative risk measure for all studies combined. For this example, relative risk values that are to the left of the center line represent a result in favor of azithromycin. The plot allows us to visually understand the inconsistency in findings and large variance in several studies for this review. Because there are so many differences in study designs and methods of data synthesis, there is always a question regarding the sensitivity of results of a systematic review. That is, would the conclusion of the review be different if the method of analysis was changed? Sensitivity analysis is a technique that assesses if findings change when key assumptions or decisions differ. For systematic reviews, these key assumptions include the criteria for inclusion and exclusion studies. For meta-analysis, this process also involves reanalyzing data using different statistical approaches or accounting for inconsistencies in reporting of results in individual studies. Papenich and others performed a sensitivity analysis for their study of the use of azithromycin for acute respiratory infection. Their analysis included studies with variable sample sizes, so they decided to do a sensitivity analysis by first omitting the single largest study with 770 subjects to see if sample size made a difference in outcome. For the remaining studies, with samples between 50 and 350 subjects, they found a relative risk of 1.06, which supported the original findings. They continued their sensitivity analysis by focusing on 3 studies that had sufficient concealment of allocation. This analysis resulted in a relative risk of 0.52. For the remaining 11 studies with inadequate concealment, the relative risk was 1.14. The authors suggested that the reduced relative risk with concealment indicated the azithromycin reduced the risk of clinical failure in patients with respiratory tract infection. The authors therefore concluded that the drug was effective based on the greater validity in the studies that showed a stronger effect. If the sensitivity analysis does not show substantially changed results, it strengthens findings in the meta-analysis. When the sensitivity analysis leads to a different conclusion, the interpretation should be more guarded. Because systematic reviews and meta-analysis are being seen as the highest form of evidence in a literature search, we must take responsibility for critical appraisal of reviews to determine if they are valid in their presentation of findings. We have to assure ourselves that the authors of the review have done an adequate job of locating, summarizing, evaluating, and synthesizing the information that we will use for our clinical decisions. A useful checklist has been developed to guide the reader in this process based on 3 areas of concern. 1. Are the results of the study valid? 2. What are the results? And 3. Will the results help me in caring for my patients? Refer to Table 16.8 in your textbook.